My name is Dalala Raja, and today I'll be presenting work I've done jointly with Antoine Cailloux and Axel van Lamsveer on adapting requirements model to varying environments. Full knowledge of environments in which software operates is not always available at design time, especially where these can change due to unanticipated events, where different services are needed for different customers, or as new regulations and standards are introduced. These require the software to adapt to such changes. Let's, for instance, take the problem of designing an urban traffic control software for enforcing low emission zones. Such software is often designed for environments where polluting vehicles such as buses are present, or in some cases other vehicles like cars and motorcycles. But the way in which LES is enforced can vary from one city to another. Let's take, for example, the case of London and Brussels. A software designed for London should recognize that polluting vehicles are allowed within these zones, but must pay a daily charge that depends on the vehicle type. So motor caravans pay £100, whereas buses pay £200. It should also recognize that a fine is issued for those that don't pay the charge, and this fine depends on the vehicle type or the time elapsed since the fine was issued. So the fine for a motor caravan is £500, unless it's paid within 14 days, it's £250. However, this software couldn't be deployed immediately in Brussels, where it's assumed that polluting vehicles are not allowed within the LES zones, and that the fine for entering depends on the fuel type, the Euro standard of the car, and whether it's a repeated offence or not. So in this case, the requirements for the London software must be adapted to the Brussels context. Existing approaches that aim to address this or similar problems can be classified into three main groups: requirements adaptation, dynamic software product line, or requirements evolution. The main limitation, however, is that they assume that the space of possible variation is known in advance, explicitly modeled, and can't be easily changed once defined. We instead propose a formal approach to the requirements adaptation problem at design time, where the adaptation process is driven by satisfaction arguments, which require low-level, context-dependent goals to achieve high-level goals that are common across the context, and the adaptations are learned from the new environments, but don't change requirements unnecessarily, making only local changes where needed and generating similar variants of the software where possible, but also ensure that the adapted requirements adhere to the software capabilities. To represent requirements, we adopt the goal-oriented framework CHAOS, which enables their formal specification and analysis. For the purpose of the presentation, it's enough to know that requirements are modeled as goal graphs, and high-level goals are gradually refined into lower-level ones until they can be assigned to individual agents, and children goals at any one depth are consistent and until their parent goals, in other words, complete. Goal dependencies on the environment conditions are also captured explicitly in these models. In this setting, the aim of our methodology is, for a goal model of a particular source context, for instance the London context, adapt the problematic requirements in this model to suit the Brussels context, while preserving high-level common goals and ensuring that the semantics of these refinements are correctly maintained. I'll briefly describe three key steps of our approach called RESPIRE. Details are in the full paper. It first builds a reference model from the goal model of the source context, the environment conditions of the target context, and the agent specifications, which describe what each agent can monitor and control. The reference model has as its root a goal to be maintained across the two contexts, which we call an anchor goal, and whose refinements include goals that are subject to adaptation, in this case the London goals, and where the source's environment conditions have been replaced with those of the target context. The reference model then undergoes an iterative adaptation process. This is based on a counterexample guided learning loop in which adaptations of the reference model are learned from counterexamples to the model's correct semantics. The loop starts by verifying the semantics of the refinements in the reference model, which basically means model checking the sub-goals against the parent goals. RESPIRE reduces the number of verifications needed significantly by checking that the leaf goals entail the anchor goals. If not, the counterexample generated illustrates the need for adaptation. To guide the adaptation towards similar variants, RESPIRE also generates examples demonstrating how the original leaf goals could satisfy the anchor goals in the new environment. In our example, the first check shows the need for adaptation. A lorry running on diesel enters the LES zone and is not issued a fine. This tells us there's a problem in the model. but where is it, and how do we resolve it? Do we rewrite the specifications, or do you change the refinement relations, and if so, in what way? Respire answers these questions automatically through a process of logic-based learning. This is a mechanism for synthesizing and revising logic programs from examples. Given a fixed theory called background theory, and a theory that is subject to change called the revisable theory, which together do not entail some observations, the aim is to find a revised theory so that the entailment relation holds. The solution space can be reduced by restricting the signature from which the revisable theory is formed and imposing costs to distinguish preferred solutions. To learn adaptations, we define the anchor goals, the agent specifications, the new environment conditions, and the goal model semantics as the background theory, since these are fixed. The goal specifications and refinement relations as our revisable theory, and the traces for the anchor goal satisfiability as examples that should be allowed in the adapted models, but those violating the anchors as ones that shouldn't. The adaptation space includes the set of new goal specifications and refinement relations that form an adapted goal model. To search for similar variants, a cost is incurred for every addition and deletion to a goal specification or refinement relation. To find local adaptations, a cost is also incurred for changing the goals that further apart. In the model, this is determined by how many refinement links are between them. The learning mechanism tries to minimize these costs. In our example, the learning generates a candidate adaptation which issues a fine for any vehicle running on petrol that enters the area. Respire checks the leaf goals in this new model against the anchor goals and finds that the model needs further adaptation. The loop continues until no further adaptation is triggered, and by that ensuring that the adapted model is semantically sound. However, the goal model could still contain irrelevant goals that refer to the source target. These are eliminated by a minimization procedure without affecting the correct construction of the goal model. To evaluate Respire, we built a prototype tool in Python which uses third-party modules of model checking and learning. The tool keeps the engineer in the loop to validate the anchor satisfiability traces, since these will be allowed by the adapted model. We consider 6 variants of the computer-aided dispatch system, focusing on 2 contexts, Belgium and Wales, and adaptations in both directions. Our choices of the adaptation problems were guided by the kinds of adaptations needed. In all cases, Respire was able to compute similar and local adaptations, where only a subset of the goals needed adaptation, minimization removing irrelevant goals. Now, we found that longer iterations were needed for adding refinement relations compared to deleting. Further studies needed, however, to understand correlations between adaptation strategies, number of intermediate adaptation computed, and the final cost. But generally, we found that the time taken to compute these adaptations was relatively small, which is promising. So in summary, we've proposed a new approach to requirements adaptation at design time, which is driven by satisfaction arguments, where the adaptation space is not explicitly defined in advance, and the adaptations that we compute are local and similar. For this, we've developed a new counterexample guided learning approach, which considers user-defined quantitative objectives for locality and similarity. We're currently looking at extending this approach to runtime by integrating controller synthesis and looking at ways which we can allow a system to degrade when no adaptations can be found. Thank you very much for listening.